So, welcome back. Last video we have seen how to solve a wave equation in the full domain as a d-element solution, of course with initial data, and then on a semi infinite domain 0 to infinity with initial data and a boundary condition at x equal to 0. So, you can give, you have given two boundary conditions, one is the displacement is 0, other one is the slope is 0. For these boundary data, the boundary value problem, initial boundary value problem is solved just by extending as even or odd function to the full domain, and you make use of d-element solution. That is what we have seen. We also have seen for the full domain, we have shown that the solution is unique. Okay. So, before I do a more general approach, suppose if you give the boundary condition as a different one, non-zero boundary condition or a combination of u and ux. Thus, for example, you say u plus ux equal to 0 at x equal to 0, u at 0 t plus dou u by dou x at 0 t. If this is 0, then we cannot simply extend as an even or odd function, this will not work. So, what we do is a more general approach I will try to give you today, but I will not do for this generalized new boundary condition. Instead, the approach will be given for the same boundary conditions of what I have done for earlier. So, that is u at x 0 is 0, u at 0 t is 0 at x equal to 0, okay. U at dou u by dou x at 0 t is also 0. So, that means at x equal to 0 you give u is 0 or ux equal to 0, okay. For these two boundary conditions I give you the new approach, so that this approach you can apply to any boundary initial value problem. So, where the boundary condition can be combination of u and ux, or you can take non-zero boundary condition like u at 0 t equal to some arbitrary function, you can give p of t, okay. So, that before I do this, let us move on to show that problems on the semi infinite domain is unique, okay. So, what we do is if you consider, I will just explain you briefly, if this is not an R, what you do is if your wave equation is on a semi infinite domain, that is x belongs to 0 to infinity, in that case the energy is same. So, the total energy is the same expression, and the initial value problem you have to change. So, only change here is x belongs to R you have to replace with 0 to infinity, and you give the boundary condition, okay. So, the boundary condition when you give, what is the change? So, the proof is, to show the uniqueness, you assume that u1 and u2 are two solutions of the problem, okay, not this problem now. Now, you consider simply x belongs to 0 to infinity, and you give the boundary condition. Boundary condition is u at 0 t is 0 or ux at 0 t equal to 0. So, either one of them, okay. So, assume that u1 and u2 are two solutions of this problem now, then you can see that the difference is also satisfying the wave equation, this equation in this domain, and the difference w at x 0 is 0, wt at x 0 is also 0, because it is the same f. u1 at x 0 is fx, u2 at x 0 is also fx. So, the difference is 0. So, this is same, only thing is boundary condition will change, it will not be changed, here also it is same. So, w at 0 t is 0 or wx at 0 t is also 0, okay. So, this is what becomes, you have a w that satisfies the difference between two solutions, the difference of two solutions, if they are distinct, the difference satisfying the wave equation, these are the initial data and this is the boundary data, okay. So, you consider the same way, so everything is same. So, you consider the same total energy as the energy function of t, and you know that initially at 0 at t equal to 0, because of the initial data, and this is 0, okay. That implies because energy is conserved, so you have for all times this has to be 0, and this is also same. So, this implies this is true. no, I think not there, but here. So, here onwards you have to do. So, we will start from here. So, this is the boundary, this is the you start with. So, what is the energy here you have to see, okay. So, we will first show that the energy is same even when the wave equation is given on a semi infinite domain. So, x belongs to, instead of r, now you have from 0 to infinity, okay. So, earlier you have r, okay. So, I do not want to remove, so this r or 0 to infinity. So, let us say 0 to infinity, what happens here? So, you have a kinetic energy is same. So, instead of if you consider this one, if you consider x belongs to 0 to infinity. So, you have to consider this kinetic energy is half mv square, instead of from minus infinity to 0 infinity, you have to do it from 0 to infinity. So, this is your kinetic energy. So, this is your kinetic energy. So, you take the derivative and you have this one. So, you have, instead of minus 0 to infinity, so you have this one, okay. This is the change of kinetic energy with time, is the derivative of kinetic energy is this. Now, you do the integration by parts, that is what you have done earlier also. So, if you do this, this is what you get. So, what you see that ux at infinity is because displacement or slope has to be 0 at infinity. So, this is 0, but at 0 ux at 0, if your boundary condition is ux is 0, then so for the semi infinite domain, if your boundary condition here is ux is 0, then anyway 0, there is no issue even at x equal to 0. Suppose u is 0, u at 0 t is 0. Here if this is given, clearly ut of 0 t is also 0, because you take this as this is a function of t which is 0, whose derivative with respect to t is also 0. Now, this implies, if this is your condition, this implies ut at 0 t is 0, also 0. So, that makes it 0. So, in any case this will not be there. So, in this case for the semi infinite domain, you have, this is your total energy, okay. So, this is your total energy, and total energy now is potential energy now 0 to infinity you can define. So, that your total energy is simply from 0 to infinity, 0 to infinity. So, whatever may be your boundary condition, either this or this, if this is the case, directly this is becoming 0, there is no issue. But if suppose the displacement is 0 is given as a boundary condition, and you can see that time derivative of it is also 0, because u at 0 t as a function of t is 0, if you differentiate with respect to t is also 0. So, because of that you have ut here, so that will also be 0 at x equal to 0. So, there is no issue even here, okay. So, this is what, so the total energy is like this. Now, you consider this initial value problem on the semi infinite domain, and now u is 0, either this boundary condition or this boundary condition you consider, and u1 and u2 be two solutions of the problem. If you consider the difference of that is w, we call it w, and w satisfying the initial condition, 0 initial conditions, and the boundary condition is either of them. Now, you consider this, this is same. Now, only thing you have to write it as total derivative. So, energy function of t is now from 0 to infinity to this integral, this is the kinetic energy and this is the potential energy. So, that is the total energy. Because of this initial data, this energy is at t equal time t equal to 0 is 0, because of conservation of energy this has to be 0 for every t. So, rest is same. So, the gradient of w has to be 0, because for all times if this has to be 0, the integrand has to be 0, each of them, that is nothing but your gradient. So, it implies it is constant, because the w is 0 at t equal to 0, okay. W, that is w at wx. So, from here, from the initial data, w at x and x is equal to wx, dou w by dou x, x0 is 0, and anyway second initial condition will give you wt at x equal to 0 is 0. So, from that you can say that w at x equal to 0, okay. So, this has to be constant, and gradient of w is 0 for every x and t, implies wxt is constant, this is same, okay. So, w at x equal to x0, this we know, okay. W at x0 from this initial condition which is 0. So, that implies w at x. So, that is a constant, this has to be same for all t. So, this is 0 at t equal to 0, that implies for all t you have w x equal to 0, that implies u1 equal to u2 for every x and t. So, the same proof is true even if you take the boundary condition either 0, w is 0, displacement is 0 or the slope of the string at x equal to 0 if you consider as a boundary condition, still uniqueness of the solution is guaranteed for this initial boundary value problem for the wave equation in the semi infinite domain 0 to infinity. So, now so you have a unique solution. So, D'Alembert solution is the only solution for the initial value problem for the wave equation on the full domain minus infinity infinity. On a semi infinite domain, if you consider these two boundary conditions u equal to 0 or ux equal to 0, you have shown that you have given a solution and that solution is actually unique by the same energy argument. That is what we have just seen. Okay. Now, I will give you a more general approach if you replace these boundary conditions. So, if you have a wave equation like this, uxx equal to 0, x is positive and t is positive, this is your domain, and initial value is u at x0 is fx, ut at x0 is gx as your initial data. Boundary data, if you have instead of earlier boundary condition, instead of fixing and freeing, instead of having this string edge as a fixed one or a free one, that is u at x0, u at x equal to 0, u for all times you are fixing it as 0. Okay. This is what we have seen earlier, or u at ux at 0 t, this is a free edge of the string, this is fixed edge. Okay. What else? We can also have more generally, you can have 0 t equal to some function of t, p of t. Okay. So, this to in order to solve this problem with this boundary condition, or u at 0 t plus some k constant times this plus ux at 0 t equal to 0. For this boundary condition, combination of these two, this and this combination if you take, you do not know how to solve, because this just by extending as a even and odd function will not work. So, you need more general approach to treat this problem. So, what we do is, now this is your domain, x is positive and t is also positive. So, you have, this is a quarter plane, this is x and this is t, and you bring your xi and eta variables as xi equal to x minus ct, eta equal to x plus ct. You consider this new variables and your equation becomes u xi eta, that is what you have seen, equal to 0. Okay. So, wave equation becomes this implies u at x t is the general solution of the wave equation is c1 x minus ct, where c1 is arbitrary function plus c2 of x plus ct. This is what we have seen. So, right now you try to apply your initial condition now, and clearly what you have to observe is x is positive and t is positive. Earlier x can take any value, now x is only positive and t is positive. So, what is required here is x plus ct, because x is positive, t is positive, x plus ct is always positive because c is speed of the wave, so that is constant, that is positive anyway. Okay. But x minus ct, once you fix your x value which is positive, and for bigger times, for at larger time, this x minus ct becomes negative. So, you need c1 function for the should be defined, you want c1 function of x for x less than 0. So, you need to find this function if you want a solution. If you want a solution, that satisfies the initial condition and the boundary condition. So we have already seen that how to apply the initial conditions. Okay. Let us make this initial condition. First, initial conditions gives u at x0 equal to fx. Okay. This implies this is c1 x plus c2 x equal to fx. Okay. The next one is ut at x0 equal to gx. This will give me minus c times c1 x minus c2 of x c2 dash, okay, equal to gx. This is what we have seen earlier. If you apply this one, you can get this. Okay. Now you take the difference. Now if you simply, now this one you simply integrate it. So if you integrate this one, you will see that c1 dash, or you can write c2 dash, c2 of x minus c1 of x equal to 1 by c g of x. This you are integrating from g of x is s ds. This is from x naught to x. Okay. If you do this difference minus this is going to be plus. So you have c2 at x naught minus c1 at x naught. This is an arbitrary constant. Okay. Call this k, some arbitrary constant k. So you have, this implies c2 of x minus c1 of x is nothing but 1 by c. This c is actually small c, that is speed of the wave. So this is from x naught to x g of s ds plus k. K is an arbitrary constant. K is arbitrary constant because you do not know c1 and c2. So c1 and c2 are arbitrary functions. Fix those function value at some point, it should be arbitrary constant. So now considering this one and this one, these two equations, you can add and subtract to see that c1, if you add it, you will get c2 of x equal to 1 by 2 fx plus 1 by 2c x naught to x g of s ds plus k by 2. So this is what you get if you add, and if you take the difference, you will get c1 of x, 2 times c1 of x equal to, again later on you divide with half. So you have a half fx. Now you are taking the difference. Okay. This equation, first this equation minus this equation. So you have 2c1. So you have here minus 1 by c. So you after division 2c integral x naught to x g of s ds, and you have a minus k by 2. So these are the two equations you will get. Okay. But I need, so this is c1x and c2x. So the general solution is here. You want c1 x minus ct. So you need to find c1 even for the negative values, because x minus ct can be negative. Okay. When x minus ct is negative, when x is less than ct, x is positive, we know. So x is so if you want u of xt for x equal to something, you need, so for x positive you can clearly see that the solution is you need c1 at the negative values. Okay. So what we do is we apply. So this is what, if you want these negative values for this function, that will give you this, that can be gotten from this boundary condition. Okay. So I use this one. So I use this boundary condition to get these negative values, whatever you required for the solution. So let us see how we do this. U at 0 t equal to 0. Okay. So this implies Now, the general solution is this. From that you can see that C1 minus Ct plus C2 Ct equal to 0. So, this implies C1 of minus Ct equal to minus C2 of Ct. Okay. So, you want basically in your solution u of x t C1 of x minus Ct. So, you just write C1 of, so this implies this is like C1 of xi, if you call xi as not xi, let us say some other variable, okay, some L, C1 L is minus Ct. So, that is nothing but C2 of minus L. So, in the place of L what you actually require is for the general solution C1 of x minus Ct. So, the place of L if you put x minus Ct is equal to minus C2 of minus x minus Ct. So, that is Ct minus x, okay, that we know from here. So, that we can write it now, that is half times minus, in fact minus half f of Ct minus x minus 1 by 2 c x naught to Ct minus x, wherever x is there you replace Ct minus x, okay, and then minus k by 2, that is my C1 of x t. And you know what is your C2 of x minus x plus Ct, that is what is required in your general solution. So, C2 of x t you can get it from here directly. So, that is half f of x plus Ct plus 1 by 2 c x naught to x plus Ct g of s ds, here g of s ds, okay, and then plus k by 2. This is directly from the same C2. So, this implies what is my u x t? U x t is this one plus this one. So, that will give you, so half f of x plus Ct minus f of Ct minus x, okay, and plus 1 by 2 c this plus this. So, this is from Ct minus x to Ct plus x, that is x plus Ct of g of s ds. So, this k by 2, that k by 2 cancels. This is when did I use this? This is when I have C1 is negative, C1 for negative values, C1 this is for L negative values, okay. So, when I will have x minus Ct is negative, that is 0 less than x less than Ct. So, in this case x minus Ct is negative, that is this argument is negative, that is my L is negative. So, when L is negative I use minus C2 of minus L, that is what you have, okay. So, this whatever you have written I use C1 function for the ordinate for the negative values. So, that is only if x is between this one, and for x greater than Ct you do not have to worry about anything, you can directly write when x is greater than Ct both are positive. So, you know C1 C2 both are positive. So, you can directly get from here, okay, C1 C2 directly substitute, that is same as half f of x plus Ct minus f of x minus Ct plus 1 by 2 c x minus Ct to x plus Ct g of s ds. This is exactly what we derived earlier, okay. This is the solution for this initial boundary value problem that we are talking about, okay, a new general approach. This is general approach to solve the wave equation when on the semi infinite domain 0 to infinity, okay, and this is the boundary condition we used, fixed edge. For the fixed edge This is what we found. Okay. So far, if you want this to be, this is what you, this is how you derived, but the thing is, you have, if you want the u to be to solution, f has to be twice differentiable function and g has to be once, it should be differentiable and continuous function, because u is a u x x, this g is, then only you get g x. Okay. If you differentiate u twice with respect to x, then you have to differentiate this g with respect to only one differentiate because of this integral. Okay. So, you have, if you want this to be a solution of the wave equation, f should be twice differentiable. If you can write it, if u is a solution, the above. Okay. If u is a solution of if u is the solution, because we have seen that this is the only solution, it has only one solution, u is the solution of the problem, then f must be f is twice continuously differentiable and g is continuously differentiable function. That means f double dash and g dash, f dash g dash are continuous, it should exist and continuous functions, that is what it means. And also again they have to be that, and if you make use of this continuity, if they are continuous, you make use of this, u is continuous, u of x t is continuous at x equal to c t. Okay. If you use this, you will see that f of 0 has to be 0, you will get, and if u x or u t of x t is continuous at x equal to t, c t will, if you actually use this expression and differentiate and make it equal at x equal to c t, you will see that g of 0 equal to 0. So, these are necessarily you have to satisfy, the initial data has to satisfy. This is exactly what we were what we have solved earlier by considering by taking an odd extension, immediately you see that f of 0 is 0, g of 0 is 0. Okay. The way you have extended odd extension and your initial data has to be twice differentiable, because it has to satisfy the wave equation. So, that is how this is like going in a reverse direction, but it works, is more general, because in the same approach if you apply for the other boundary condition, so it will work for any boundary condition. So, the approach is this, you start with a general solution of the wave equation, you take this initial data, you have these two equations. Okay. Now, only thing is when x is because x is positive, when x is positive, x minus ct can be negative. So, for those values, that is between 0 to x is between 0 to x ct, this can be negative. So, at those negative values you can, that is given by the boundary condition. The boundary condition will give you that CL, L is negative. Okay. If you apply the boundary condition, that is actually giving you this negative values of C1. So, that I make use and then finally add it up when x is between 0 to Ct, and when x is greater than Ct, you do not have problem. When x is greater than Ct, both are positive and you already have, so you do not need boundary condition. Okay. So, you simply use the initial data, this is what you get and you simply add it, you will get it. So, that is the solution you get, okay, for x greater than Ct. Now, if you want this to be, this is how you constructed, if you want this to be a solution, if you want this to be a solution of your wave equation, and f has to be twice differentiable and g has to be one time differentiable function and it has to be continuous. So, by using continuity of u at x equal to Ct, you will see that f of 0 is 0, ux or ut is continuous at x equal to 0, x equal to Ct will give you g of 0 is 0. So, the initial data has to be, it is like an odd extension, when you do the odd extension you see that f of 0 is 0 and g of 0 is also 0. Okay. So, what we do is in the next video we will try to do the same technique, this more general approach for the other boundary condition, that is free edge, that is ux equal to 0. if you use this ux equal to 0, how we can do the same thing, same technique, and that we will see in the next video. For the free edge ux equal to 0, as when you consider this as a boundary condition for the wave equation on a semi infinite domain 0 to infinity, we will try to give you the same approach that we have seen just now. We have seen just now this is the more general approach. So, what we do is we will try to see this solution in this approach in the next video. Thank you very much.